Okay, now on torsions, we have book examples on torsions. So this is the first example. So here, a solid shaft of 120 millimeter diameter is required to transmit 200 kilowatt at 100 RPM. So with the power and the speed, the first thing is to calculate the torque. So based on the power transmitted formula, which is 2 pi nt over 60. So from here, you will be able to calculate the torque. Power is 200 kilowatt here, okay, and the speed given here is 100 RPM. So the torque would be equals to 19.1 Newton meter. Sorry, it's kilonewton meter, okay. So I put kilowatt. This is my mistake. Yeah? So the torque, so you have 60 times power, that is 200 times 10 to the power of 3 divided by 2 pi, and the speed is 100 RPM. So you have your torque as 19.1, okay, kilonewton meter. So then we know that, okay, based on the questions, we either refers to stiffness relationship. You still remember we have stiffness relationship and strength relationship. So that depends on what are the data that is given in the question. So in this question here, they have given us the angle of twist, and then they have given us the modulus of rigidity, that is the uppercase letter G, that means the symbol G. Okay, so the only relationship that we can use based on the given data is the stiffness relationship. So that is T over J equals to the G theta over L. So I have to redo the arrangement here. So T represents the torque, J is the second moment of area or the moment of inertia, G is where you have your modulus of rigidity of 90 gigapascal, theta is the angle of twist, 2 degrees, make sure you convert to radians, and the length, okay. So the length, find the length of the shaft. So the question is actually wanted us to find the length of the shaft. So first, we have already got the torque. Then the next is the second moment of area. So this is a solid shaft. So for the solid shaft, remember the moment of area, the second moment of area. For a solid shaft, that means a circular solid section. So it's given as pi d4 over 32. So the diameter is 120 millimeters, so it's 1.12 meter to the power of 4 divided by 32. So that is your polar moment of, second polar moment of inertia, or the second moment of area. Then the angle of twist, this is in degree. Remember, if we were to substitute it here, this part here must be in radians. It shouldn't be in degree unless you have a sine, cosine, or tangent with the angle theta, then it can remain as degree. So now this is not, and so must convert it to radians. So divided by 180 or 360, up to you. Then if it is 180, you must multiply by pi. If it is 360, then you must multiply by 2 pi. So then you got your angle of twist in radians. So once you have got all this, substitute it into the formula to find out the length. Okay, so the length is required. So substitute G, that is 90 giga, so times 10 to the power of 9. Angle of twist, we have found here 0.0349. And then the second moment of area, 2.036 times 10 to the power of -5. And then the torque, so that is 19.1 kilonewton meter. So that is why it's multiplied by 10 to the power of 3. This is kilonewton meter, it's not kilowatt. Okay, I remind you one more time. So the length found is 3.365 meter. That is what the question wanted us to find. So this is the first part. So usually we start out with easier examples, okay? So the next one, now the first one is based on solid shaft. Now the second one is based on a hollow shaft. So this is a hollow shaft. So find the angle of twist per meter length. So that means you have to find theta over L. Theta over L, find the angle of twist per meter length. Theta over L. So theta is the angle of twist, L is the length of a hollow shaft of 100 mm external diameter and 60 millimeter internal diameter. So therefore, when you refer to your second moment of area, you must use this formula. It's not the previous one where it is pi d4 over 32. This one you have to take into account of the section or the whole, okay, so which you must minus, so minus d4. So this lowercase letter d is actually referring to the internal diameter. The uppercase letter d here, it refers to the external diameter. So remember, if you want the unit of the polar moment of area, second moment of area in meter to the power of 4, because everything here is in meter, especially when you refer to the G, is in gigapascal. It's actually giganewton per meter square. And then the shear stress is megapascal, which is meganewton per meter square. So based on these units here, their basic units, you have a meter inside. So that is why it is advisable that your diameter has to be converted to meter as well. So 100 mm, so 0.1. 60 mm, so it is 0.06 to the power of 4 over 32. So that is your second moment of area, or the second moment of inertia. So the torque, oh sorry, jumbled up the whole thing. Now we use strength relationship. Why strength relationship? Now you see, now we have only strength relationship and stiffness relationship. So you have to choose whether you're going to apply strength or the previous one, that is stiffness. Okay, that is stiffness. So in this case here, we will be using both strength and stiffness. Okay, so strength, based on strength, okay, you have T over J, shear stress over R. So the shear stress is given. So you can use your shear stress here, 35 times 10 to the power of 6. The J, the polar second moment of area, also we have found. That is 8.545 times 10 to the power of negative 4. And then the radius. This radius here should be the maximum radius, because you are looking at maximum shear stress. This is a maximum shear stress because they say not to exceed 35. Not to exceed, that means it is the maximum. So 35 megapascal is the maximum radius, maximum shear stress. So if you were to refer to maximum shear stress, make sure the diameter that you refer, or the radius that you refer here, also must be maximum. So that is why the radius that we consider here is the maximum radius, not the 30 mm, it's the 50 mm. Okay, so bear that in, remember that. Okay, so you have this. So then substitute your shear stress. There's your shear stress. That is your radius or diameter. Oh, this is again my mistake. Should be 0.05. So I will have to point out my mistake here. So this is 0.05, not 0.1. Okay, 0.05. So when you refer to the podcast again, okay, please, this is referring to 0.05, and the top won't be 299. Okay, so the J is 8.545 times 10 to the power of negative 4, because 0.1, that means it's based on 100 mm. That is the diameter, it's not the radius. So your radius must be 50 mm actually. So this must be actually 50, that is 0.05, not 0.1. So you will get your torque value. If you change this, then you get a different value of torque. So once you have got torque and J, that means the polar moment of inertia, then you use the stiffness relationship. Why? Because they ask us to find the angle of twist per meter length. So the only relationship that has the theta and the L with it is the stiffness relationship. And only with the strength relationship you have the shear stress. So from this you make use to find out the torque, and here you use this to find out the answer for theta over L. So torque, G and J. So you will get your angle of twist per meter length at 0.2359 degree per meter length, or it can be expressed as 0.00412 radians per meter. So I hope you know how to convert radians to degree or degree to radians, please. Yeah. So from radians, if you want to convert to degree, you must multiply by 180 divided by pi. Okay, so that is the other way around. Okay, now that's all for this part. So what you have to do is you have to, now I have done question 2 and question 3. So what you have to do is you have to go back and do question 1. So that's all for this section. So you have another work example later on, another one afterward. Okay, thank you very much.